Now that we have established several powerful properties of the Riemann integral, we can tie it back to the axiomatic characterization that we saw way back in the very first module in the series on Riemann integration. So, recall that in the very first module we had considered a function of the form IAB of IABF that associates with a function. So, f from AB to R is a continuous function, and IAB of f is sort of a function defined on continuous functions that assigns a number. And this number satisfies these two properties, that IAC of f plus IBC of f is equal to IAB of f, where A is less than C less than B. This is one of the properties. And the second property is that, or rather this was the second property. So the first property was that if m is less than or equal to f of x is less than or equal to capital M on this closed interval AB, then small m b minus a less than or equal to integral, not integral, I AB of f is less than or equal to capital M into b minus a. Okay, now we have established that first of all continuous functions on closed intervals are Riemann integrable. We have already established this. Then we have also established that the above two properties that uniquely characterize IAB of f is satisfied by integral a to b of f. So that means that this is the unique function. On continuous functions that satisfies the axiomatic characterization. So this says that the function IAB, whose existence was up in the air, is now no longer up in the air, it's on concrete. We have created the appropriate definitions that will make IAB exist. And this existence is shown to be nothing but the Riemann integral that we have been studying. Now this helps us a lot because the topic of this module is the fundamental theorem of calculus. We have already done the hard work. So I can state the fundamental theorem of calculus. now. Theorem of calculus. If f from AB to R is Riemann integrable or is continuous, I got ahead of myself. The version I was about to state is going to be left to you in the exercises. If f from AB to R is continuous, then g of x equal to integral a to x f is a differentiable function, on closed interval AB, and g prime of x is nothing but f of x for all x in closed interval AB. This follows immediately because we have already proved this, that any IAB that satisfies these two conditions is automatically going to satisfy the conclusion of the fundamental theorem of calculus. We have already seen that, so this bit is done with zero effort. Furthermore, if g is any function any function on closed interval a b such that g prime of x is equal to f of x, then integral a to b f of f is nothing but g of b minus g of a. Okay, so what this says is integration is the opposite of differentiation. So if you start with a continuous function, take any antiderivative, that is a function g such that g prime of x equal to f of x, then integrating a to b f is reduced to finding the function g and then just substituting the limits to get g of b minus g of a. Okay, so because we have that integration and differentiation are opposites, several useful things like integration by substitution etc. can be justified now. You have never formally seen a justification of these facts, but we can do them now. So let's see, let's call these applications. Oh, by the way, I should remark, the way I have stated the fundamental theorem of calculus, I have stated it only for continuous functions, even though you can say a lot more which is there as part of the exercises. Since the crux, the idea of the proof is there already in the axiomatic characterization, and all you have to do is adapt the proofs and modify it a little bit. I'm just stating it in this case. In any scenario, this is the most important version of the fundamental theorem of calculus, so I'm leaving it here. Okay, so in the exercises, please look at modified statements of the fundamental theorem of calculus, which applies to Riemann integrable functions, not just continuous functions. Before we begin with the first application, let me just give a definition. If a is greater than b, then we define integral a to b f to be minus integral b to a f. This is the usual definition. So exercise, which is not that such a difficult exercise, see which properties. So let me just put by definition equal to, see which properties, or rather identities of Riemann integral continue to be valid. With this more general definition. With this definition out of the way, let's see some applications. So application 1. This application is also called the change of variables. So this states the following: let a comma b and c comma d with a less than b, c less than d be closed intervals, and let f from ab to cd be a continuously differentiable function. Recall, this just means that the function is differentiable and the derivative f prime is continuous. Let f from cd to r be continuous. Not f, g. We have already used the letter f. Let g from cd to r be continuous. Now the question that this change of variables seeks to answer is integral f of a to f of b g. What is this going to be? Note, there is no necessity for f of a to be less than f of b. It could be the case that f of b is actually less than f of a. That's why I had to make the definition that I just made before I started with this application. So integral f of a to f of b g, as you all know, is nothing but integral a to b g of f of x f prime of x. Okay. Okay. So why is this true? Let's see a proof. Let's see a proof. Now let capital G be an antiderivative of G on CD. Okay, such an antiderivative exists because the function G is given to be continuous. Then notice that G composed with this F, G composed with F will be an antiderivative for the function G of f of x, f prime of x. This is just chain rule because G composed with f prime is just G prime of f of x times f prime of x, and G prime of f of x is nothing but G of f of x into f prime x, right? So G composed with f is an antiderivative for G of f of x, f prime of x. What this says is integral a to b f composed with G of x, G prime of sorry, I completely reversed the thing, sorry about that. G of f of x, f prime x, integral a to b of this is nothing but G of f of b minus G of f of a. Okay, so this is just an application of the fundamental theorem of calculus. This is just an application of the fundamental theorem of calculus. Please look back in the original modules on the axiomatic characterization to see why this follows from the fundamental theorem of calculus immediately, or better yet, just sit down right now and prove it. It's just going to take you 2 minutes. So integral a to b G of f of x, f prime of x is just G of f of b minus G of f of a, which is nothing but integral f of a to f of b, f of a to f of b of G of x, just G. Why is this the case? Well, again by fundamental theorem of calculus, because integral of G f of a to f of b will be just capital G f of b minus G f of a, and this is same as this. Okay, so this is the famous integration by substitution, change of variables. There are several names for this: integration by substitution or change of variables, and the proof just follows immediately from the fundamental theorem of calculus. That's application 1. Let's see application 2. Application 2 is one of the most powerful methods of integration that you have no doubt extensively studied in high school. This is called integration by parts. What does integration by parts say? Let f comma g from ab to r be continuously differentiable. So take two functions f comma g on the interval ab that are continuously differentiable. What you are interested in is integrating f g prime from a to b. Okay, as we all know, the answer to this is nothing but f of b, f of g of b minus f of a, g of a minus integral a to b. You just reverse the derivatives, that is, it becomes gf prime. Okay, you're all familiar with this. Integral a to b fg prime is fb gb minus fa ga minus integral a to b gf prime. If you're looking at this and thinking that it's different from what you saw in high school, the only reason is because in high school you would have seen it in this form. Integral fg is integral fg prime is fg minus g prime f. You would have seen it in this form, or integral u dv is uv minus integral v du. Okay. Now these are just antiderivatives. These are the antiderivative form. The antiderivative form, where I'm treating integral of f as meaning taking antiderivative. As meaning to take antiderivative. That's the only reason why this form might look, the form that I have stated, integral a b f g prime is f of b g of b minus f a g a minus integral a to b g f prime, that might look slightly different. Well, how does this follow? The proof is very easy. It just applies the famous Leibniz rule for differentiation of product. We already know that fg prime is f prime g plus fg prime. We already know this. So integral a to b fg prime is going to be integral f prime g a to b plus integral a to b fg prime. Okay, from which it follows, from which the result is obvious. The result is obvious. Okay, so two famous theorems that you have used left and right in your high school and probably in your undergraduate studies to evaluate integrals, that is integration by substitution and integration by parts, can both be easily justified as simple consequences of the fundamental theorem of calculus. So let me end with making some remarks. There will be some reference in the notes. Note that one of the consequences of the fundamental theorem of calculus is that every continuous function has an antiderivative. But if you just talk about elementary functions, which we are going to define very soon, elementary functions, these are functions made out of, I'll put this in quotes, made out of polynomials, trigonometric functions, exponentials, logarithms, quotients. If you just look at a function that is made out of this, by made out of I just mean by adding, multiplying, subtracting, composing, so on and so forth. If you just look at these functions, these are called elementary functions. I will not give a rigorous definition. I will leave it to you to check the reference in the notes. If you just look at elementary functions, suppose such a function is continuous on the closed interval a b, then there is no guarantee that its antiderivative is also going to be an elementary function. We know that there is an abstract antiderivative that comes for free from the fundamental theorem of calculus, but it could get really complicated. It might not be an elementary function at all. So don't make the mistake of thinking that just because you are given an expression that it will be easy to find what the antiderivative is. That's not the case. No doubt you still have nightmares of very complicated substitutions that seem to be pulled out of a magic hat to make the integral work. That is really needed simply because there is no algorithm to integrate in any easy manner. Please check the references if this is interesting to you. This is a course on real analysis and you have just watched the module on the fundamental theorem of calculus.